Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about deep learning and some computer vision applications and see how could we apply deep learning and the networks that we learned in computer vision applications. Okay, so we already know about deep neural networks for classification, so we want to know what other tasks are exist to use the deep learning. So as you could see, for classification we could use AlexNet, Resonant, VGGNet, and other neural networks that we talked about them. Let's see other tasks are prevalent in computer vision. So the first thing is semantic segmentation. So in semantic segmentation, we want to annotate labels that belongs to different objects. So for example, in this case, we have sky in here. We have another object in here, and so on. Okay, so we want to label all of the pixels. The second task is classification and localization. So we want to both know what is the object in this image and where is it. So for example, in this image, if you use AlexNet, for example, it will tell you probably you have a cat in this image, but also you want to know where is the cat, or you want to know, in other words, you want to know the bounding box, which you could describe that with x and y and a width and height for this bounding box. Okay. The third task is object detection. So in this case, you have multiple objects, and so it is an extension of classification plus localization. So you maybe have different objects or multiple objects in an image, and you want to localize all of them and know what is each of them. Okay. And the last task is instance segmentation. As you could see, we want to segment different instances of objects from an image, and again we could have multiple objects in the image. Okay, let's go on. So the first idea is actually to use semantic segmentation. For semantic segmentation is that we could have we could actually label each pixel to specify what is that pixel. So we could extract a patch in the neighborhood of a pixel, and then pass this patch to a CNN. It could be AlexNet or whatever. After that, we could label that with whether it is cow, grass, or everything else. So we could label all of the pixels with just considering one patch around them and pass them through the network. But this is so inefficient, right? Because we should use sliding window approach for each pixel, which could have computational cost a lot. Okay. The next idea is to use a fully convolutional network to get the output. So we could design a neural network, a CNN, that has some convolutional layers, as you could see in there. And after that, for the last convolutional layer, we could have C channels. So in this case, to get the output, we have C is the actually number of instances that we have. For example, if we have cow, grass, and sky, then C should be 3 in this case. Okay, so now if I have 3 different channels for a specific height and width, then I could take the maximum of these. So if the maximum neuron in here is this one, so I put grass, which I could specify that with green color in here. Okay, so I could place green color in here instead of this row and column. Okay, so this is actually getting an argmax in the channel wise to get the output. Okay, so it is one idea, but the problem with this way is that it is too expensive, because the image is actually probably is a large image, and applying convolution in different layers could be computationally expensive. A better way to do that is having some kind of downsampling structure and then upsampling it again. So in this case, we could split this CNN into 2 different subnetworks. So the first subnetwork first extracts some features by downsampling the image. After that, from these features, another network tries to, or the second subnetwork tries to reproduce the semantic segmentation map. Okay, so in this case, the number of parameters are less than this case, and also the computational cost is less than the first case. Okay, but the problem in this case is that how should we perform upsampling? How we know that when we apply convolution to a layer or max pooling, we are reducing the resolution. So if we have something like this, we end up with something smaller than original feature map. Then if we have something like this, how could we upsample these feature maps to get larger feature maps? Okay, so there are different methods to do this. The first method is that actual nearest neighbor, which you could, let's say we want to convert 2x2 feature map to 4x4. So we could use nearest neighbor. So we put all of the 1 pixel in here to its neighbors. Okay, and so on. So, but it could be not a very great way to do upsampling. Okay, maybe we have another good methods. The next method is to just use 0 in the neighborhood of one pixel that we have. Actually, it is not the neighborhood, because we place that pixel in the corner of other pixels. So as you could see here, also this way is relatively an easy way to do upsampling. The next thing is max onpooling. So in this case, when you are doing max pooling in your network, you should remember the positions of the max pooling that you do. For example, when we are applying max pooling in this case, we should save the location of these maximum values. Okay, now when we have something like this and I want to unpull this or upsample this 2x2 feature map, I could place this pixel to the corresponding max pulling layer that I saved that before. So I place one here because in max pulling I had the maximum value in this position, okay, and so on, okay, and except of them I place 0. Okay, but in this case actually maybe it is a little hard or a little difficult to save all of the positions, and you should always have a 2x2 mapping for every max pulling and max unpulling, and also it could not be very effective. The most recent way and to do the upsampling is the transpose convolution, or sometimes it's called deconvolution, which is a really bad name, because deconvolution is a really another operation, but it is actually a transpose convolution, not deconvolution, but sometimes it's called deconvolution layer. Okay, so in transpose convolution you are doing exactly transpose convolution instead of convolution to get a bigger feature map. Let's see whether we could show that. Maybe in here for a 1D example, let's say this is the input and this is the filter. Okay, so because we have deconvolution or transpose convolution, let's see in here also other names of transpose convolution. So the people say deconvolution, which is a bad name, up convolution, fractionally strided convolution, and or backward strided convolution. But transpose convolution and deconvolution are the most widely used names for transpose convolution. Okay, so in this case we have a filter, okay, and it is actually learnable. So it is great about deconvolution or transpose convolution that filter is learnable, and we could train that filter. So in the unpulling, in the max unpulling or other nearest neighbor upsampling and so on, we couldn't train those upsampling methods, but in here the filter could be learnable. Okay, so let's say this is the input and we have a filter like this, XYZ. To get the output, as you could see, we are blending this input with filter like this. Okay, so we have AX, AY, AZ plus BX, and BY and BZ. Okay, I hope that this makes sense. For 2D example, I found a very great post and stack exchange, which is really great. So in 2D case, as you could see here, this is the filter or kernel that you want to use, and this is the input. So if you have a 2x2 input, then you could get the output. So first you should just pad your input with zeros, okay, and then apply this filter on your input. In this case you are enlarging your input. Okay, now you have 2x2 transpose 2x2 feature map in here, and you get 4x4 output feature map in there. And also you could use different strides for your deconvolution to get larger output. Okay, so with transpose convolution you could enlarge the feature maps. So we apply convolution and max pulling in here, and we could apply deconvolution layer or transpose convolution in these layers, okay, to get the output. Okay, let's go to the next task, which is classification plus localization. Okay, in this case, we have different classes and we want to know where is that object. Okay, so for each data we have a class and a bounding box which we could specify with x, y, width and height of this rectangle over there. Okay, and for the evaluation metric for the classification is accuracy, which we know about it, and the evaluation metric for localization is intersection over union, or IOU, which tells us how much we accurately localize that object. So how much, let's say this is the ground truth and this is our prediction, and so we want to know how much they have intersection. Okay, so as you could see, this is the name of intersection over union. Okay, so the first thing that we could do to do the classification plus localization is that we could use a pre-trained network like AlexNet or Resonant on that they are pre-trained on ImageNet as feature extractor. Then we could get a fully connected layer for class score with softmax loss, or in other words, you are applying a softmax activation function in here to get the label of the image. And also you have another fully connected layer to extracting box coordinates, okay, which you have x, y, width and height, and you want to predict this. And for this one you should use categorical cross entropy, and for this one, for predicting the bounding box coordinates, we should use L2 loss, or basically if the output of network is x and the ground truth is xg, we probably use this one, right? So which is L2 loss, and the total loss of the network is the sum of the categorical cross entropy or classification loss and the regression loss. Okay, and we train this network. Okay, so this is a simple recipe for classification. So you could train, or as I mentioned, you could download a classification model which is pre-trained on ImageNet, for example VGG or Resonant, and apply and get or attach a fully connected layer to get the class scores. So that was for classification. And for regression, you want to have 4 different outputs. So first you apply a neural network to extract some features like VGGNet or other things. After that you apply a fully connected layer and get the L2 loss. Okay, so we could see a summary of that network in there. Okay, and also sometimes you could actually freeze this part. So if you have not very large data set, you could just freeze this part and just train this part of your network. Okay, so in order to get the classification scores or box coordinates, you could just train these fully connected layers instead of training all the network. But if you have a relatively large data set, you could just initialize your network with VGG or other weights of other networks and then retrain all of the network. Okay. Another network that maybe is good to talk about is human pose estimation. So in this case, we want to estimate the pose of a human. Okay, so now in this case we have different for left foot we have an L2 loss, for right foot we have L2 loss, and so on. Okay, so the total loss will be the sum of all of the losses. Okay, so now you should be able to design different networks for your task and use the different losses to combine them. Okay, and different networks actually use different kind of attaching the regression head at different positions. For example, overfit, which is not actually related to overfit. The overfit is a network that is proposed by Google, and it is quite a good network. And in VGG and overfit, they used here for using the regression part, but in some other networks like Deepose or RCNN, they apply fully connected layer, and after that they get the regression head. Okay, so it is not really, I think, important in our discussion. So you could actually read papers about the best result, or you could just try them yourself. Okay, so now we want to talk about object detection. Okay, so in object detection, let's see the deep neural network, and before deep neural networks and after deep convolutional neural networks accuracy. So as you could see in here, we have traditional methods in object detection, but when people use deep convolutional neural networks, the accuracy start to increase again. So maybe you think that object detection is like regression, but the problem is that in object detection we may have different number of outputs. So for example, in this case we just have one output. Okay, so if you define your network with just one regression head, which gives you X, Y, W, and H, you could predict that. But maybe in another image you have 3 different objects, so now your network could not handle this case. Okay, so we should propose a method to be able to handle this. Okay, the very first idea that come to my mind, or come probably to your mind, is that we could apply sliding window approach to check whether each patch has, or each window has, what kind of object and where is that. So in this case we could use the same network. So first in here we answer this question, that what is this object and where is it. And so we could actually continue this process to find this dog, this is dog, and this is here, and this is dog, this is cat, and this is dog. Okay, and also we could have background class to train the network. Okay, but in order to do that, the problem is that because we should do that in different scales and at different locations, so we have to test these patches and also these patch sizes and so on. So it is really computationally expensive to use sliding window for object detection. So we should propose another method. Okay, so the method that is proposed, the first method is in fact was region proposals. So for region proposals, in fact, it says that instead of using all of the image for a sliding window, there is a method which we don't want to talk about it, but there is a method to get some region proposal for the objects. So instead of having lots of different windows, we just have limited number of windows, so like 1000 regions for this image. And after that, we could use the same thing. So we call this RCNN. So let's see how it works. So we first find region proposals, or ROI means that region of interest from a proposal. Then we resize all of them to the same size because we want to pass them to CNNs. After that, we pass all of them through a convolutional neural network, and they are the same network, so we pass all of them to a network, and we have an SVM. Let's say this is a fully connected layer with hinge loss. Okay, so we call it sometimes SVM loss as we talked about it. So it tells us whether that is a background or cat or dog. Okay, and after that we need another loss function for telling us that in fact to refine this box. Okay, so in fact, let's say the region proposal is here and we have a cat, maybe it is, I don't know, it is a cat or not, and this bounding box regressor tries to refine this by extracting a more fine bounding box. Okay, so in this case we could use this network to for object detection. Okay, and there are some approaches to do training faster, but in fact this method requires lots of space, and the training is really slow, and in the test time or for the inference it takes 47 seconds approximately per image, which is a lot, which is really insane nowadays especially. So we should use another methods. So the other method is fast RCNN. So in fast RCNN, instead of passing each proposal in comparison with RCNN, that we extract all of the region proposals and apply convnet to that patch. Now we just pass the whole image once through the convolutional neural network. Okay, so instead of passing all of the patches for, let's say, when we have 1000 region proposal passed each of them to the convolutional neural network, we should do that 1000 times. Instead of that, we just pass the whole image through a convolutional neural network just once. Now from this feature map, from the resulted feature map, we could extract some region proposals now, okay? And again, we have from those feature map that have region proposals, we could have softmax classifier for classification part, and we could have a regressor to refine the bounding boxes. So the point of Fast CNN is that it shares the computation of convolutional layers between different proposals. Okay, so the training is much more faster than the RCNN. Okay, and let's see, this is an example of RCNN with another method, SPP and Fast RCNN. So in Fast RCNN, as you could see, the test time or inference time is much more less than the RCNN itself, okay? And also the training time, which for RCNN is 84 hours, and it is much more faster, okay? But in another method called faster RCNN, we could make the network to extract a region proposal without any external modules or without any external approach. Let the CNN to extract the region proposals. Okay, so we have a region proposal net to extract the proposals, and after that we have the same thing for classification and regression loss. Okay, so we have a region proposal network to extract region proposals, and after that we have another network to get the object location and the object class. Okay, and as you could see in here, for faster RCNN we have a really good improvement in comparison with fast RCNN. So, but actually there are lots of other types of object detection neural networks. So for examples, in modern convolutional neural networks for object detection, like YOLO, we have they are much more faster than also faster RCNN. Okay, and there is a trade-off between the speed and the accuracy. So the faster RCNN is sometimes slower than some methods, but it is more accurate, so you should note those. Okay, and this is an example of object detection. So this is a resonant backbone, which so a network that its backbone is resonant, trained for object detection. It is it seems so fun. And for instance segmentation, you could see that you could take a look at actually the mask RCNN, which is not have a really new thing, that you could actually take a look at their paper. So we have a similar thing, and it gets a very good result for instance segmentation. So maybe you want to use that in your applications. Okay, yeah, that's it. Now you know about much more about computer vision applications of deep learning, and I hope you enjoyed from this session. And don't forget to just practice this in Keras and try to implement these networks or find these networks in GitHub and retrain them. And so because the implementation of these is so important. Okay, see you in the next session. Bye.